Yeah. Hi. Today I would like to introduce our recent work online man to web. Yeah. Recently we all know that various agent framework have emerged based on the powerful large language model and the vision language model. Those agents help users solve all kinds of daily tasks by browsing and interacting with the website, such as booking flight or finding top-rated restaurants. However, we all know that existing benchmarks still have several limitations, like still using the offline citing. But as CX paper mentioned before, actually there are multiple paths to complete the task, so which means that the evaluation based on the ground truth trajectory is unreliable. Moreover, such a static environment fails to capture the challenge of the real-world dynamic website, such as all kinds of pop-ups.
Mm.
And here, for example, Visual Web Arena use a sandbox environment to mimic the real-world website. However, the simulation website is clean, simple, and free of any pop-ups, which makes it much easier for agents to complete the task. In contrast, the real-world websites are much more complex with more advertising and function that significantly increase the interactive elements. Also, real websites usually have pop-ups, which can also cause the agent to be stuck. Therefore, there is a huge gap between current benchmark and the real world scenarios, which means current web agents may not be as strong as the paper report. We may also have overestimate their capability. So we need a new benchmark that reduce the gap to the real world website. Even some benchmarks use online environments, it still lack of the diversity and cannot reflect the real world user task as well. Though even for the same task, different websites may need to different difficulty. The existing benchmarks only include a very small number of the websites, which cannot cover the website that the user often uses in the real world. For example, the Visual Web Arena only covers 3 websites, and Web Voyager only includes 15 websites. The same with the Man to Web Live. It contains 100 tasks across 14 websites. Uh, Web Voyager is the most widely used benchmarks. However, it synthesizes the task using a large language model, which may lead to simple and a lack of the diversity of the task. To quantify this observation, we develop a simple two-step search agent. Firstly, it just generate a query for Google search, and then it collect into a link to check the answer without performing any further actions. When we evaluate such a simple search agent on the web version, we can find that such simple agent can already achieve a 15% success rate, which suggests that the tasks are easy and many can be addressed using shortcuts like the Google search rather than navigating on the website. Therefore, a better online benchmark for web agent is needed to bridge this gap. We introduce a new benchmark online man to web that contains 300 diverse and realistic tasks, covers 136 popular websites. It's also challenging that a two-step search agent can only solve the 20% of the task, showing that most of the tasks cannot be solved by taking shortcuts. We also categorize tasks into 3 different difficulty level to better evaluate the fine-grained performance of the web agent. Yeah, building on our data set, we conduct the first comprehensive and rigorous evaluation of the several state-of-the-art agents. We evaluate 6 popular web agents, including the operator and the Cloud 3.7, and we evaluate the result manually. We can see the figure here. There is a huge gap between the online match web and the popular, widely adopted web voyager. For example, browser use agents even reach 16% gap. This result indicate that the current agents are still unable to solve the real-world task effectively. And the existing benchmark are overestimate the performance due to the simple and the lack of the diversity. Yeah, breaking down to a fine-grained performance, we can find that there is also a significant drop in the performance of the task complexity increased. Specifically, the average success rate decreased by 13% when moving from easy to medium task, followed by an additional 15% drop from medium to hard task. So this result demonstrates that all current web agents struggle to solve the harder task. Yeah, in fact, we cannot always introduce human evaluation, which is time intensive and labor consuming. And also this method is not scalable. Therefore, one of the biggest challenges is how we can build a reliable evaluation method to evaluate the performance of the agents on dynamic website. Yeah, and after we do some survey, we found that current auto evaluation methods are still unreliable. Yeah, for example, the rule-based method in Mind2Web Live requires designing specific keynotes such as the URL for each task, which is not scalable. Moreover, due to the website updates, the previous keynote are out of date, resulting also unreliable. And some benchmarks use LLM's judge to do the auto evaluation, but they are still unreliable with a high rate of false positive. To be more specific, autonomous evaluation work. This is a paper. This is a work from the Berkeley's. Yeah, they only consider the final screenshot and overlooks all previous screenshot, which means that in this way, it will lose some important information. For the web voyagers auto evaluation, it just input all kinds of screenshot at once, which will lead to the issue of token overhead in the model. Because some agents, like the operator, based on my experience, it tends to produce the 100 screenshot for one task. So it means it will input 100 screenshot into the model. Therefore, we propose a more reliable auto evaluation called web judge that only keeps the key screenshot in the final input. We ask the model to score each screenshot and then retain only the important intermediate screenshot and just drop any an irrelevant screenshot. Yeah, our approach mainly has 3 parts. The first step is key point identification. The second is key screenshot identification. And the final step is outcome judgment. The first step is just to let the model identify the necessary key points for completing the task. And the second step is just to keep the important intermediate screenshot. Finally, the elevator will output whether the agent complete the task successfully. Yeah, here is the experiment results. Yeah, we can see the results from table. Web judge can achieve a high agreement rate of 87% with the human judge, as well as a small gap of the 4%. And this result demonstrate that the effect demonstrate the effective lives and the reliability of the web judge. Yeah, we also compare the web judge with existing evaluation methods. We can see that the web judge consistently achieved the highest agreements and outperforms other methods. It also our web judge 7 billion model trained with the Q1 2.5 VR model also outperforms 4 mini with an average of the 18.7 agreement rate. Yeah, and to further demonstrate the generalization ability of the web judge, we evaluate it on a recent work called Agent Reward Bench, which contains 1,300 trajectories across 5 popular benchmarks like the Web Arena, Visual Web Arena, Assistant Bench, and Work Arena, and Work Arena Plus, as shown in the table. Web judge significantly outperforms existing method with a high precision, which means that it holds potential as a robust and scalable reward model for the downstream applications like reinforcement learning and self-reflection. Yeah, meanwhile, it also achieves a small gap than that of the rule-based method, suggesting that web judge is a reliable automatic elevator for all kinds of tasks. Yeah, we also conduct a detailed analysis on their advantages and limitations, thereby shedding light on the further improvement. We first analyze the advantages of the operator because it represents the state-of-the-art performance among existing web agents. Yeah, to be more specific, unlike other agents that rely on broad keyword queries, operators usually apply the filter and structured search. Here's an example. The task is about finding certain TV. The operator just select each requirement using the filters instead of inputting all keywords into the query like the cloud computer use. And another advantage is diverse action space. It can use a set of tools to help it better solve the task. Yeah, like the Control plus F to do the search. Yeah, here's an example. The task is about to compare two cars, and the operator can directly use the Control plus F to search to help it located the function. And also operator also demonstrate the self-verification and the self-correction ability. It's a very powerful ability that we haven't seen in other agents. This is an example of such powerful ability. Yeah, given the task of the funding clause, the operator plans to select the black, but due to a grounding error, it select the blue by mistake. But then it found this error and correct it by itself and then reselect the black color. Yeah, although operator has certain advantages, it also exhibits several limitations. It is sensitive to numerical and temporal constraints that are required in the task. Here are several examples. So this is the first example. The task is about selecting the flag from certain term, and it cannot select the correct term. And this is also a task that the operator select the wrong range of the term. The task required is to select the 2004, but it just select the 2001.
So soon we have to also move on to the next talk. So could you try to?
Okay,
Yeah.
this is a final example. It also applied a wrong filter with the 0, but the task required $25. Yeah, that's it.
Okay. But these were nice examples.
Thank you.
Yeah, so thanks a lot. And we do the discussion after all the small talks. I mean, talks, right? So short talks, I would say. So yeah, thank you so much for presenting the work. It's super insightful, and I have a lot of questions, but I'll leave that for the later part of the session. And
Yeah,
now,
sure.
please, Sherzod, would you like to share your contribution, please?
Yeah. So I decided to use the paper actually to discuss about it. I think this also is quite possible, right? So we included some nice examples so I could go through this. So our paper is called Plant in Cupboard, Orange on Rably, Inat, Aphone. So if you cannot understand it, I will explain what that means. So it's about benchmarking incremental learning of situation and language model using a text simulated situated environment. So this is a joint work done by Jonathan Jordan, myself, and David Stangen at University of Potsdam. I think the easiest way to explain is actually to look at this example here that we have included. The task is actually just text-based. So there is an agent that is put in some sort of a room, and the room is provided with such an information saying that the goal, put the potted plant on the table. And this is the additional information that is given here saying you're in a living room. There's a cupboard, a table, a chair. The cupboard is closed. There's a passage to the hallway, to a kitchen here. The goal of the agent is obviously to navigate, basically going to the kitchen, to hallway, or whatever. So this is a interactive fiction environment that you might have seen before. So that's kind of an environment that we have built, and it's only text-based. So what initially you see, we can see as humans, basically this is the initial state that the agent is in. So these are the connected rooms. Obviously, this information is never revealed, as you can see in the first task, right? And then let's assume that our agent is quite intelligent and says, go to hallway, right? And we can see that from here, living room, that's where the agent initially is. You can go to the hallway. So it's now the agent is in the hallway, then agent gets a feedback for every action, basically. Saying you're in a hallway now, there's a potted plant. The potted plant is on the floor. There are passages to a bedroom, living room, and broom closet. And so as you can see, basically giving the information of this one. And then the agent says, yeah, take the potted plant, go to living room. Every time the agent makes basically generates a command, the environment gives a feedback. If agent says something like drink water, the agent would say this, and then environment would say, I don't know what you mean, because drink water is not a viable action in this given environment. So that by doing this incrementally, that's what we call incremental learning. And then there's a situatedness, basically the agent is situated in some sort of environment. We expect the agent to figure out what is the best action to go based on the feedback that is given by the environment. So in this case, obviously we have put a perfect example, but obviously the agents are not all perfect like this, so that it went to the hallway, picked up the potted plant, brought it back to the living room and put it on the table. And then the agent has to also say that I'm done. So this is a requirement from our environment here, that if agent doesn't say that I'm done, so agents have to be kind of a self-aware of their action space and saying that I have finished the task and then I'm done. The task basically finishes here. So how we did this is we have, as I mentioned maybe before, but I can explain again, we have a framework called ClemBench, which I can quickly go to the reference. So the reference is here, basically, and then we implement dialogue game using our existing framework that allows implementing dialogue games quite easily. And what we implemented here, what we call is adventure game. Adventure game is obviously based on an interactive fiction game. There's a part about, so it's basically agent making a kind of based on making prediction based on the policy. It's observable Markov policies and so on. But the main point is there's a game. It's an agent here is an LLM, obviously. An agent is given at some sort of a prompt text to interact within this environment. And what agent has to do is output in this format, starting with this prompt symbol, and then some sort of a natural language command. And then the environment, the dialogue game has an interpreter, which basically parses this natural language command. And if this is a viable action, then it proceeds to do that action. And when you do this action, the game state, the world state changes. If you say you go to the, from the living room, you go to the hallway, the agent's position basically changes, right? When you say pick up the plant, the state of the object changes, meaning the plant is now located within the agent. And if the agent if agent generates some sort of a natural language command that is not viable in the environment says, I don't know what you mean. So that's basically what it is. And everything the agent has to do is incrementally learn how to interact within this environment by using what LLMs really have is in-context learning abilities. There's basically both of these things. On the top is incremental learning, because agent might doesn't know what to do initially, but based on the feedback incrementally, we just want to basically benchmark whether they get to the goal state or not. And to do this, we have implemented a set of nice experiments, which I would give in a list here. Let's go first here. And we have benchmarked a set of LLMs that are both from commercial and also from the open side. So the first one, we called it basic, which is a basic interaction. The example that I showed earlier is given a goal, there are different difficulties, easy and hard. We just increase the path that the agent has to take within the hard. And we also sometimes put the object that they have to basically bring it back to a certain place is, let's say, some sort of a container like a cupboard or whatever. Okay, so sometimes the objects are not directly observable when the agent goes to that room. That's how we try to make it this. Then we have something called pre-exploration. Pre-exploration is we automatically traverse the map there, and we provide this as a context in the beginning. So basic starts from nothing. Pre-exploration starts with basic information about where the rooms and how are they connected, and basic objects that are observable, basically. We just want to see here whether, given such a head start of information, whether the agents can actually get efficient because you already give kind of the map of the rooms and so on, right? And which objects are there. Then a very simple thing we did is we put a limit on the number of objects an agent can carry, because some of these other levels require the multiple objects to be carried from one place to another and so on. And the last thing, this is the most interesting part, is since the example that I showed up was all English, now we created new synthetic English, pseudo-English words by using English grammar, but they basically mean completely different things. So I can show some examples from this basically here. So instead of the agent has to, in normal basic experiments or other experiments, the agent had to say, for instance, put the book on the shelf, right? And now the agent has to say, Aphone dekte on stort. So we basically replace the normal English words with this. And our goal here is to see, again, incremental learning, whether they can learn incrementally over time how to say these things. Because we do provide this information in the beginning, saying that whenever agent, we say that we give, here we have 3 different levels. Here we provide a short explanation of an action word, such as Aphone and so on. Then we have another medium level where we do the same thing. We create, so we use the existing scripts here. We created new pseudo-English words that are never seen before. And then we have something like NS means close, Pante means put, Inat means open. Then in the hard level, we basically do not provide any information about which action words are there. Okay, we don't do this, but we do give obviously some basic information when agent enters some sort of room and so on. So
is that a real language or?
It's not a real language. It's just a pseudo-English language. So it mimics English grammar to some extent, like a stemming and so on is not the same. Obviously, there is no such word, but it kind of goes in the same, let's say for instance, stuff like this, motor subst, and the subst can be dent and so on. Yeah, so it's completely new words. And the reason we're doing this to ensure that they were never part of the training data of these LLMs. Right? If they're not part of the training data, then we can basically test their generalization abilities and their incremental learning abilities all together without having any bias of the training data that they are trained on. Okay. And this is basically why we have implemented these 3 normal English words with a different conditions. Some of them are controlled, right? We have a controlled, meaning you have a limit of maximum 2 objects you can carry. Or other one was pre-exploration. We give the basic information about the map. And the 4th one is synthetic words experiment.
Interesting.
All right, so then we did this. Let me show you first the overall comparison of the LLMs. So these results are averaged across all 4 experiments. In total, we had 144 instances here. Okay, and then this is basically the agent allowed to play the game with this dialogue game for maximum 50 turns. Okay, you have to finish the given task within 50 turns. If you don't finish, what we call is we stop the game automatically. So meaning that is not really, that's called what we call aborted games. So here we have some metrics. So the main metric here is a CLEM score, which is a combination of a quality and the played. Played is very simply did the agent follow all the rules to every point, meaning it has to give an output starting with some action verb and so on. It has to stop the game on its own, right? So that's what we call played, meaning it followed all the instructions to the end. Quality is how good the task was solved, basically, to what extent. So usually we have 1 to 3 objects to be carried from place to place, right? And then that's how we measure. And then CLEM score is a combination of both, meaning we just multiply them. And to our surprise, Claude 3.7 got the best score of 86. And the second one was O3 Mini, which is 68. And the GPT-4 was even lower than the 52. But then the best open weight model was 43. So here you can see a stark difference between open weight model and a commercial model. There's a difference of 43 points, basically. Right. So this is our basic idea of benchmarking. And then we can go to these results here to have a little bit more in depth on this. So more or less all the models to some extent can do some sort of this task, right? So basic task is navigating somewhere, picking up the objects, bringing it back, and so on. So they can do this. In the hard cases, we can see that, for instance, in the Llama 3.1, the score from 62 drops to 31, meaning the hard cases are actually difficult for it. But Claude doesn't care. Claude gets even better in the quality on this one. Okay, so pre-exploration, idea was that we wanted to see whether models can get better at this task, right? Because we already give that there is this room, there is that room, and so on and so on. There are these objects. Then we see that the good models, so Claude and the O3 Mini, so Claude actually gets better on this compared to the basic one here, right? And we can see that there's improvement in the hard example. The tasks are all the same. We just put the conditions on them. Okay, so then we see that in a good performing model, we see those improvements, right? But in the models that don't really perform that well in the beginning, for instance, this is a DeepSeek version 3. So basic experiment got, let's say here, 62. And once we give pre-exploration, it actually drops, meaning giving useful information doesn't really help the model to navigate the task and solve it. Okay, so this is what we see here. And then the most important thing is obviously here, the interesting part is synthetic words. Here we see that Claude basically just crushes everything here. So the word that I've said about this, Aphone, the stead room or whatever that we basically call them now, is Claude solves everything in the easy level. And it solves everything in the medium level. In the hard cases, it only misses 1 episode out of 16. So this basically shows that the model can generalize to new conditions, can generalize to words that were never seen before by the end of this training data, and incrementally can learn the meaning of those words by interacting within the environment, and the environment giving a feedback on this. So this actually shows kind of what we would like to see in some sort of these models, basically generalizing to unknown conditions completely. And when we look at the OpenAI is one of the best models, we see that there's a definitely huge difference between Claude performance and the O3 Mini, and the same holds for GPT-4o. Right. So the point here is that we wanted to measure the situatedness, action prediction, incremental learning abilities of these models, and then that's what we did. And the last thing, I just want to show you one graph here that's kind of shows the efficiency of these models. So what you see here is that these are the bars are for each high-performing models. The first one is the Claude O3 Mini, and each of these bars are the experiments and average number of turns. Basically, how many turns does it take for each experiment? We just average them. Okay, so here, for instance, the blue one is the basic. So the Claude takes on average around 20 turns to finish that task. Then we have drawn these two horizontal lines. The first one is average. So average, we also can calculate optimal number of turns an agent requires to solve that task, because we can calculate them, right? So that's what we put here. These are the optimal values that model can do. On the bottom, this is the synthetic words one. Okay. Now, given that those are the optimal values, we can see what the models do, right? And we can see that good performing models, they're kind of close to the optimal line, but not on the synthetic words. And this is what we actually wanted to see, because obviously these tasks being English words, the models already know what put, what go, and what pick up means. But here in the task of synthetic words, it obviously takes longer than the optimal value, right? On average, because they have to figure out the meaning, they have to infer the meaning of those words by just interacting and incrementally learning the meaning of those words. And then when we look at why Claude is so good, it's also good in performance, but it's also actually quite efficient in this task. And then we can see that O3 Mini takes quite a long time to figure out the meaning. And this actually explains why some of these models actually also performing worse, because they're not really efficient, and they're also lacking performance basically in the task. All right, so I would say I have examples as well, but maybe if there's any need, I can get back to this again. I have some qualitative examples here as well.
Cool. So that's it, or
I can explain these examples if you want to.
Or we can also, I mean, it's also nice to have more conversation, right? So
yeah,
maybe we can also kind of jump into more discussion mode. And but thanks a lot for sharing the contribution. It's super cool, and yeah, I'm curious to know more about the work here. So how it works is we kind of open the stage, right? And we do discussion basically. I also try not to ask a lot of questions myself, because I kind of I have a lot of questions naturally, but I also try to kind of encourage the audience, or basically the speakers to ask each other.
A quick question.
Sure.
Yeah. Hi. Actually, I don't know how to pronounce the name. The professor. I just want to ask. So, for your paper, the results, experiment results are based on the large language model rather than the vision.
Yeah, the task is completed text-based, so it's a text-based environment.
Okay,
yeah.
So I'm thinking that if we can just transfer the task or the instruction into the image to help the model understand the task, so how will the performance change when we just transfer the task to the image?
Yeah, so you can't transfer the task, right? In the end, like if you would put me in such a room, right, I would, if I get some feedback from the environment, right? In this case, we just wanted to, because if you include the image side of the LLM or MLLM, multimodal LLM, there's a limitation on the image side as well, so that might be a limiting factor sometimes, because we have done this another work on this. The finer the details get, the worse the LLMs are. So if you have 15 different very small items in the background, LLM may not even see this at all. Okay.
Yeah, I agree. Yeah.
Right.
But
so that's
why we want
to separate image side, because image is actually limiting factor here, right?
Yeah, I agree. And actually, recent model like the O4 Mini or O3, the model can zoom in to figure out the details of the image, but I'm not sure whether it can help them figure out
No,
the
the
details.
O3 Mini doesn't support images. O3 Mini is text only model.
Or maybe
So
that's O4 Mini.
it's a reasoning model, but it's text only reasoning model.
Okay, yeah.
So the GPT-4o has a text component, but sorry, image component. But yeah, in here we just wanted to separate the basic limitation, which is the vision can be limiting factor for performance. We just wanted to evaluate how good are they in general if you give this information, right?
Yeah. Thanks. Yeah, that's very cool.
Which actually kind of makes me wonder about your paper, right? So in the end, you're using both image and text together, right?
Yeah. We include
so
text.
the same thing I can ask you as well. So do you think image could be a limiting factor in the web tasks? Because, you know, like not every web page is built the same way, right? Sometimes information is hidden or whatever. How do you see about this?
Yeah. Actually, for the website, there are a lot of interactive elements. So the model with the model cannot do the correct action with low resolution. So you must input a lot of image token to improve the image resolution to help the model better solve the task. So this is why the recent OpenAI models like the O4 Mini powered by the zooming technique to help the model figure out the details. Yeah, in general, this is one of the biggest challenges that the current model faced. It cannot see some small element or solve the pop-ups. Yeah.
Mm-hmm.
Yeah, that's a good question.
Interesting. That also kind of makes me wonder. So I see that in the space, these big tech companies are kind of big players in developing sort of state-of-the-art methods and so on. So how do you kind of harmonize your own contributions with those superpowers?
Yeah, actually, this is a good question. Yeah. Browser use is not developed by a very large company, but I think the first step is just the open source, let a lot of engineering to help you build your product or the agents. And then it can reduce the gap between the company. Yeah, I think the open source is one of the most important step. Yeah, for developing the agents.
Yeah, I can add on that as well. So, I mean, that's the reason why we started this kind of a lot of research projects that we're working on the benchmarking. And so we wanted to measure basically how good are they, right? And we started this exactly 2 years ago in 2023, May. That's what we started with our first EMLP paper. That was original Clembench paper. And then we built a lot of things around it. So building dialogue games and so on. And there we just wanted to measure how good are they. And because we were impressed, obviously, with the ChatGPT, right, when it came out, and then there was a ChatGPT-4 and so on. And when we measured that initially, the performance gap was huge. Like the one was 10% and the commercial models were 60 or 70.
Okay.
And then over time, we kept our effort going on for the past 2 years, and we keep our benchmarks up to date. We have also something called trend graph, where we can see the performance rise of open weight models and the commercial models.
Interesting.
So on average, they are catching up. So they're not there yet. They are catching up, obviously, and which was not there at all initially. Like 2 years ago, 2023 May, there was basically no competition. And then Llama models came out, and the Qwen and the DeepSeek, and this kind of a big, basically backed up by, again, industry, right? All of these models are coming from industry, so Meta, Alibaba, and so on. Okay, DeepSeek is a kind of a small company to some extent compared to them. But this basically came out there, and now they're kind of closing the gap. And we see what Tianci is also saying, that they can be also used or tinkered with to do many different tasks in which much more ease than before.
Mm-hmm. And so you have the plot where you kind of show the trend as well?
Yes, I can show that, yeah.
That would be super interesting too.
Okay, let me quickly bring it up. All right, so I will share the screen. All right, so I hope you can see it. So this is what I said about. So we have a web page called ClemBench GitHub.io, and everything we did is open source, all the framework code and so on. This is an up-to-date leaderboard, and you see here updated on May 13th.
Mm.
And so these are the models that we have evaluated very recently, and we see that there's we didn't add the latest changes. The paper that I'm presenting today is actually updated yesterday, so I released it on arXiv, very fresh. So this is text-based only. So we also have a multimodal benchmark. So here is the multimodal task. So we do have a multimodal dialog games, and then we can basically compare the performance of them. We have to update this. I think it's been some time. Last time it was updated, yeah, in March. But then here is the trend graph.
Yes.
So let's go with the text. So this is the text-only task of the trend graph. So the blue ones are commercial models, and the red ones are open weight models. You see here, that's where we started, March, right? You see, this is March, June. June. And then the performance of open weight models are increasing. So here was the Llama 405 billion, then this is the DeepSeek 3. But obviously the commercial models are also going up, right? So this is the Clem score, this is a single score that we can compare. So that now DeepSeek is at the same level that was a GPT-4 was at some time ago, right?
Yeah. So this is super cool.
And we are continuing at this effort of this basically benchmarking over different periods, just to keep track of the development cycle and see where things are.
Interesting.
Yeah, we also have the leaderboard of the web agent, but we just, for now, we just have the recent web agent. And maybe later we will add a lot of other agents.
So now that brings me to another question regarding the more meta question. I see a lot of evaluation papers, maybe for a similar reason. So I wonder whether you put efforts to kind of have more competitiveness for your benchmark. Do you try to advertise your benchmark quite a lot, or do you put any other efforts, like extra efforts, apart from just publishing papers?
I mean, we just share it on LinkedIn, but that's basically it. So we don't really put too much effort. I think there is some truth in marketing here, and in marketing here meaning I see that a lot of benchmarks that are being popular for just because popular people share it on X or on LinkedIn or reshare it or repost it. So I do see that this is being a natural way in academia, unfortunately, that the popularity still plays an important role. But yeah, what we do is we publish papers or we release them on arXiv first. If we build such a nice tools, we share them on LinkedIn, but we don't do more than that. We just hope that at some point the community will pick it up. And obviously, opportunities like this or at the presentation at the conferences is what we also do. Everything we have presented so far is a publication of some sort that we have presented at conferences. But I would say in general, I think this effect is still there of popularity. I think some people even call this Kardashian index. There is some sort of index like that. It's basically how many citations you have versus how many followers you have or something like this on those social media.
First, gain a lot of followers before publishing your paper.
Exactly. Yes.
Yeah, great.
Okay. Interesting. Tianci, do you also do any of these efforts as well?
Yeah, actually you can see our Twitter. Before we publish the paper, we also publish the blog. There are a lot of concurrent work. So if you publish the paper later, maybe some similar work will publish before your work. So your paper will lose a lot of attention. So and also just maybe 1 month or 2 months, there are several computer use agent, web agent, everyone are doing the agent. So I think you should try to do some promotion about your work to let everyone realize you publish a new work that uh, but the condition that is your work must be good for everyone to use. Yeah.
Yeah. It's not like it's just about marketing, but it's also about good work behind it as well, right?
Yeah, and also I think when you publish your paper, you should release all the things that you have, like the code, like the everything related to the experiments, so that the people can reproduce the result and do some follow-up work about your published paper.
Yeah, that's super important for benchmarks, I think.
Yeah.
But I think you have very nice tools, surrounding tools, not just the paper, but also the nice tools around it. So it looks all very good. Yeah.
Yeah, I would agree. But I feel like I think usually US being the marketing country, the best at the marketing, has some sort of traffic around its works, I would say. And the way I see it is that mostly, we also see a lot of work from Europe and then Asia being picked up, but not everything is easily picked up when some famous NLP lab tweets something, right, of their initial work, which is maybe at the same level as what you're doing, but obviously they have that popularity effect of some sort. Yeah.
Yeah. By the way, okay, so there is a question from Nobin. Please go ahead.
Hey, I have a question. It's not technical, related question. So how can I leverage, like, I'm from a pretty average NLP lab. So how can I leverage this gap with a top NLP lab and with my, that it's a pretty average NLP lab. We are only 3 or 4 people and working not so much trendy topic and moderately trendy topic. So how can I leverage this gap? Like you guys mostly are showing today web agent. That is one of the most promising frontier topic. But how can I leverage this gap?
Yeah, I think this is a general and a good question. So when your paper accepted at some conference, so you will do the poster around here. So when you present your work, like the poster, you can have more conversation with other people to promote your work, and then people will have a better understanding of your work. And if they are interested in your work, they will use your work or do some follow-up works. Yeah, I think you should try to communicate with a lot of people to promote your work.
Yeah, I think I can add on that. Obviously, promotion is one aspect, right? Either on when you go to conference, as Tianci said, presenting as an oral presentation or this. I mean, first point is you need to give a first good impression. I think that requires a little bit presentation skills and attracting people. I think this applies to every other field, doesn't have to be science. I would say that's the most important part. If you cannot understand the paper, I see people like sometimes they come and they present all the tables, every little detail of a paper, that basically you lose audience there. I would say that's probably the first, but the other thing that is basically leaving is the other resource that you share. If you share some sort of a LLM or some sort of a code that is basically there, you need to make sure that the code is compatible throughout some generations. So if you put code on GitHub, you need to make sure that it's well documented, easy to run, and also maybe living for some time, and not just that you present it, you put it there, and then you just lose interest in it. Because people sometimes write to me or to any other repositories, or like maybe 1 year, 2 years later, and so on. And this is quite common thing. So you need to make sure that the resources that you share are always available there of some sort.
Yeah, so I wanted to add one resource that I was circulating quite aggressively within my circle, which is a nice blog post on how to get a paper accepted. And it has very nice sets of pieces of advice on how to make the figures better and how to make the presentation in general better. So maybe this is also a nice way to promote your work better. So maybe with this, we have to kind of slowly close the session, because we also need to get ready for the next session, which is vision language models. I'd like to point out a few things before closing. So first of all, I'd like to thank the speakers again for sharing the work. Unfortunately, the session is a little too short. That's always how it feels like at the end. But we'll have this session on a bi-weekly basis. So in 2 weeks, we're going to have the next session again. The other thing is the feedback. We are still on the kind of the initial stage of this session. So we improve upon the previous one on a regular basis based on your feedback. So it's very important that you just share with us any of the positive or negative. Negative is also very important feedback, and we'll try to kind of improve over time. Okay, so please let us serve you better to promote your work and to promote whatever nice contribution that you have made by letting us know how we can help.